All right, let's see here. Okay, so this is the, I guess, third last tutorial, I think. So we're going to cover some FM questions, and then we'll cover the rest of the FM questions you need for the next class. And then next week will pretty much be review. All right, so I'll try to end class early, or if not, it'll just be full of review. So there won't be any more theory that's covered up, after this Wednesday. Okay. So here's the first question. So we're going to go back to basics. We're going to take a look at just angle modulated signals in general. Okay, so we've got some angle modulated signal with some carrier frequency, which we know is 1 megahertz, or it's just omega c over 1 megahertz, whatever. So it could be 2 million pi hertz, radians per second, or 1 megahertz, doesn't matter. And we have some angle modulated signal, but we actually don't know what modulation scheme to use. We don't know if it used angle modulation or frequency modulation, but we're going to take a look at both cases and go from there. Okay. So the first question asks you to find the power of the modulated signal, and that's pretty easy. Remember, for frequency modulation, you are not changing the height of the carrier. You're only changing the frequency of the actual carrier itself. So because the height of the carrier stays the same, the power is just simply the carrier squared divided by 2. It's very simple. It's like a free mark for you. All right, so A is simply, the power, right, is just simply AC squared divided by 2, or it's just 10 squared divided by 2, which is 50, whatever that is. Okay, that's great. All right, so part B. So what we need to do now is, assuming we have frequency modulation, determine what the original message signal was, and determine the maximum frequency deviation, delta F, assuming frequency modulation. Okay, that's good. All right, so if you remember the definition of frequency modulation, okay, it was AC cos and then omega CT, and then plus we had some sensitivity KF, and then integral from 0 to T M of lambda d lambda. All right? Okay, so this is the definition of a frequency modulated signal. Now, the signal that we have, it's given as 10 cos omega CT. We actually don't need to know what omega CT is, but it's 1 megahertz in terms of frequency. This is the one that we are given. So this is the problem that we are given. This is what is given in the problem. Okay, so if I compare notes, yeah. So that is what we are given. Okay, so all you have to do now is compare apples with apples. So this is our definition of frequency modulation. We just have to compare with this guy over here. Okay, so this means that KF integral this is equal to 10 sine 1000 pi t plus 20 sine 2000 pi t. Okay, so I'm going to take a leap of faith here, where if you take a look, you can see here that there is a common factor of 10. So what I'm going to do is I'm going to, actually, before I even continue, we can see here this is AC, right? I don't need to, it's pretty self-explanatory. I'm going to leave that, I'm going to leave that there because, that's common. Okay, so let me factor out a 10. 2 sine 2000 pi t. Okay, that's good. Okay, this is what I had. So you can. So let me see here. That's good. So, all right. So let's see. So we have KF and this guy. So if you take a look here, I factored out a constant. So you can think of KF as being 10 here. Okay. So I factored out that, and our message signal is simply the integral. So this is equal to this guy. So all I have to do now is. So this is what my expression was. So the integral of my message is simply sine of 1000 pi t. Sorry, let me just cross that out. 1000 pi t plus 2 sine 2000 pi t. Okay, so this is the integral of our message. If we want to find what the actual message is, when you differentiate the integral, you get the original value itself. Okay, so m of t is just the integral of the message. So we assume that one on the right side is simply the integral. So all I have to do is just differentiate the right side. So remember, when you differentiate sine, you use chain rule. So this becomes 1000 pi cos of 1000 pi t, okay, plus, and this becomes 2 times 2000, so this becomes 4000 pi, right? 2 times 2000 is 4000 pi cos of 2000 pi t. Okay? So this is our message. All right? So remember, frequency modulation, the message, when you actually take a look at it, it's the integral. So if you want to find out what the original message was, you have to take the derivative. And that's our original message. Okay, very simple. Now the next question asks you to determine what the maximum frequency deviation is. So it's simply delta F is equal to KF MP divided by 2 pi. All right? So KF, I already know, that's 10 from before, okay? And MP is the largest peak that your message signal will ever go up to. So remember that because 1,000 pi and 2,000 pi, they have a fundamental frequency or a fundamental period of 1 over 1,000, right? So right at 1 over 1,000, you're going to see both of these cosines meet up. So the amplitudes will add up. So you have 1,000 pi plus 4,000 pi, which is 5,000 pi. And so this becomes 5,000 pi divided by 2 pi. Okay, so 10 divided by 2 is 5. So you cancel the pi's out. We get 25,000 or 25 kilohertz. So this tells you that the maximum frequency deviation you'd expect, so if your carrier was 1 megahertz, then you expect it to either vary from 1.025 megahertz to 9.975 megahertz. So plus minus 25 kilohertz is what you expect the deviation of your carrier to be. Okay, very simple. Okay, any questions here? It's pretty dead simple here. You just find, figure out what the integral is and then just take the derivative of that. Okay. Part C. Oops. Yeah. Part C. Okay, good. Okay, so find the message signal, assuming it's phase modulated, and figure out what the maximum phase deviation is. So this we haven't covered before. I'm going to talk about it now, but you're not expected to know the phase deviation for the exam. I'm just going to do it because this question was asked several years ago. So I'm just going to do it just to be complete. Okay. So if you remember the phase modulated signal, it's simply the original message. So the message signal is by itself. There's no integral or anything. Okay. So if we compare apples with apples, assuming that this signal has been phase modulated, okay, so this is not KP, but this is 10 sine 1,000 pi t plus 20 sine 2,000 pi t. Okay, so what I'll do is I'll factor out that 10, right, because there's a constant that is associated with the message, so I'll have 10, and then sine of 1,000 pi t plus 2 sine 2,000 pi t. Okay, so this here is your k of p, and then this here is your message now. So we've already figured out what that is. So it's just simply this guy is your message. So let's highlight this, copy, paste, which is over here. Just get rid of this. So therefore, okay, that's good. Now the phase deviation is very simple. All you're doing is instead of KF, you have KP, and then whatever the maximum phase deviation would be, right? And then you can do it by 2 pi if you want. Not 2 pi, but you just do it like that. You don't need it to be 2 pi because they're not doing it in frequency. It's not hertz anymore. It's radians per second. You could do it in, it's radians per second. So in this case, it's just 10. And then whatever this deviation is, so remember it's going to be 1 plus 2, which is 3, so it's 30 radians per second. So this definition you don't need to know. It's just, it was part of that question that was asked when this was asked several years ago. But you don't need to know what phase deviation is. All you have to know is what frequency deviation is. That's the one that matters. Okay. All right, so C, and now D. Okay, so this question asks you, okay, so what is the relationship between the message signal assuming frequency modulation and phase modulation? Well, it's pretty simple. One is just the integral of the other, right? So if you took a look at phase modulation, if you differentiated that message, you would get what the frequency modulated message would be. Very simple, okay? So this tells you that the message signal for frequency is simply the derivative of whatever message signal you got for the phase. That's all that is. Okay, and then you can do a similar relationship where the message phase is just the integral of the frequency. It doesn't matter, but that's one relationship you can use, or you can use the integral relationship as the other. Okay, so estimate the bandwidth. If they don't ask you, you're going to use Carson's rule. That is the standard assumption. So if I say estimate the bandwidth, if it's not given to you, you're going to use Carson's rule. All right, so Carson's rule is very simple. So if you want to estimate the bandwidth of this FM signal, it's simply twice the maximum deviation plus whatever the bandwidth of the signal is, okay? So the bandwidth of the signal, let's see here. So 1,000, 2,000, yeah. So whatever. So if you take a look at our message signal here, let me see here. So okay, this is BFM. And then remember the message signal for this was 1,000 pi, cos 1,000, and then 2,000. So if you take a look at this signal, the bandwidth is simply the largest component. So remember, when you draw this, you're going to have two sets of impulses, right? You're going to have one pair at plus minus 1,000, and then another pair at plus minus, actually no, so this will be 500 hertz and 1,000 hertz. So this is 500 hertz, and this is 1,000 hertz. So the bandwidth is simply the largest non-zero component. So the bandwidth here is simply 1,000, all right? So here is 1,000, okay? This is 25,000 from before, so this is just going to be 2, and then 25 plus 1, which is going to be 2 times 26, and this is 52 kilohertz. Okay, so this 25 and the 1, this is in terms of kilohertz. Okay, so it's not actual hertz itself, this is in kilohertz. Okay, so the actual answer is 52 kilohertz. So that would be the estimated bandwidth of the signal. Okay, and that's it. Very simple. Any questions there? Good. I like that. Okay, now we're going to do some sketching, all right? It's going to be fun, I suppose. Okay, this is the next question I've got. What time is it? Good, 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 good. I'm doing a good time here. Okay, let me, good, I don't need that, so let's insert. Okay, so this is the next question that we have here. Okay. So we have an angle modulated signal. Okay, so it's usually, this is your general phasor of theta t, where theta is an angle, and then a is a constant. We don't know what a is. We don't need to know. What we do need to know is we have to sketch. Actually, yeah, we do need to know this. They usually give this to you. So this is equal to 1. Okay. So they also give you the sensitivity constant. So there's one sensitivity constant for the frequency. So this is for FM. This is another sensitivity constant for phase modulation for P of M, and then the carrier frequency is 10 megahertz. Okay, so this is our message signal here. So the modulating signal is M of t, and we have a message signal from 0 to 6 milliseconds. So this is what the message signal looks like. Okay, so our job is to sketch what the frequency modulated and phase modulated signals would look like, given that this is our message signal. All right, that's totally fine. This is the next part of the question, just to be sure. Okay, actually, there's a little bit of work on that side. So A, what are the frequencies of the FM signal at 1, 2, 3, 4, 5, and 6 milliseconds? Repeat the same for the phase modulated signals, whatever the frequencies are, and then sketch what the phase modulated signal would look like. And I'll also do the frequency modulated signal just as a bonus. Okay? All right. So, A. Okay, so if you remember, the instantaneous frequency, okay, is defined as the carrier plus your, let's see here. So this is in frequency. So we have the sensitivity and then divided by 2 pi times the message signal. Okay, so this is the definition of instantaneous frequency. So what are the frequencies? So this is instantaneous frequency. I like to point that out. But it's synonymous, because what you want to do is right at that point in time, what is the actual frequency visualized at that point? Okay, so this is actually quite simple. So let's just draw a little table, all right? So we've got, time in milliseconds, okay? We've got your message signal, and we have your instantaneous frequency, and this is going to be in megahertz, okay? So you have 0, 1, 2, 3, 4, 5, and then 6. We need to figure out what these frequencies are at each of these time points. That's fantastic. So, okay, so whatever the message signal is here, and then most of the instantaneous frequency. Okay, that's good. So at 0, okay, so at 0, the output is simply 0. Okay, so let's go through this one at a time. So remember, the instantaneous frequency relies on the message signal. So at time is equal to 1 millisecond, we see that it's 0 again. It's right over here, right? So 0 again, okay? Now if you take a look at time is 2 milliseconds, okay, it's 0 again. It's not really exciting. Take a look at time is equal to 3 milliseconds, the height is 1. Okay, there's something exciting going on, and we're going to see what's going on soon. Okay? Actually, 0 is fine. I guess it's superfluous. I don't need to do that, but okay, I'll just do it anyway. That's fine. And then for 5, we get -1, and 4, we get 0 again. So 0, -1, and then at time is equal to 6, we get 0. That's good. Right? So if you use the above equation, this is the instantaneous frequency. So at 0, we still get 10 megahertz. At 1, you're not adding the message to 0, you still get FFC, which is 10 megahertz. 2, 10 megahertz. And then finally 3, right? Remember, kf, the constant, was equal to 2 pi times 10 to the 5, right? So this becomes f of c plus 10 to the 5 m of t, okay? Because this was 2 pi times 10 to the 5. So if that cancels, 2 pi's cancel, you're left with 10 to the 5. So when the message signal is 1, I'm going to get f of c times plus 10 to the 5. And 10 to the 5 is 10 kilohertz. So you actually get 10.01. Okay? Actually, no, 10 to the 5 is, sorry, it's 100,000, sorry. So it's actually 10.1. So 10.1 megahertz goes back down to 10, and then at minus 1, you're going to go f of c subtract 10 to the 5, which becomes 9.9. Okay? And then back at 0, we get 10. Okay? So that's what's happening here. So, for any points that are 0 for the message, they stay at 10, and then the message signal, when it goes up to 1, you go up to 10.1, because 10 to the 5 is actually 100,000, all right? 0 becomes 10, and then minus 1, 9.9 again, and so on and so forth. Okay, that's good. Okay? All right, so repeat part A for the phase modulated signal. Okay, that's fine. So for the phase modulated signal, the instantaneous frequency, okay, is your carrier, and then you have plus kp divided by 2 pi. And then remember, this is phase modulation, so you have to actually take the derivative of your message signal. So this is m prime of t. All right, so this kp, if you take a look at the original question, it was 2 pi times 10 to the 2. So this is 2 pi times 10 to the 2. So basically, this tells us that the instantaneous frequencies are your carrier plus 10 to the 2 m prime of t. So whatever the derivative is at each of these points, you figure out what that is, multiply by 100, and then add with your carrier, and then you are done. Okay? So before we do that, let's actually sketch what the actual derivative will look like. So if you take a look here, let's start from here to here. Okay, so the derivative, this is slope, but this is in milliseconds, okay? So the slope here is going to be 0.5 minus 0, so you're doing rise over 1 times 0.5 times 10 to the minus 3 minus 0. So this becomes 1,000. Okay, so the slope here is 1,000. This here, you can go ahead and do that yourself. This is minus 1,000. Okay, I'll let you do that calculation yourself. Between here and here is also going to be 1,000. Okay, between here and here is minus 1,000. Right, so this is the slope. So these are the slopes. So slope, this is the slope, this is the slope. I'll let you verify that yourself, all right? So if you actually did rise over run, and if you actually did the calculations yourself, you can certainly verify that if you wish. It's basically going to be plus minus 1,000. So between 0 and 0.5, we have a constant slope of 1,000. So this is what it looks like here. So this is your derivative signal. So 0, 1, 2, 3, 4, 5, 6, okay? So we're going to fluctuate between 1,000 and minus 1,000, okay? So right at 0, there's going to be a slope of 1,000. So this is 0.5, so it's going to go here, right? And then between 0.5 and 1.5, there's a slope of minus 1,000. So this is 1.5 over here. So it's going to jump down here, between here and here, okay? And then between 1.5 and 3, there's a slope of 1,000 again. So 1.5 to 3 goes here, all right? And then between 3 and 5, there's a slope of minus 1,000. So it goes down here and then like this, like this. And then finally, at between 5 and 6, there's a slope of 1,000 again. So it goes up like this. And then it stops like that. So this is what the derivative of the message would be. So now that we have this in our pocket, all you have to do is just repeat the same table above. Instead of using the original message, you're just using the derivative instead. So let me just copy this table, and then what's going to happen is that this will, well, we're going to use the same table, but instead of using the message itself, you're going to use the derivative of the message. So this is 5, okay? And then remember, this is our equation, so fc plus 10 to the 2, all right? So all this is going to change. This is no longer valid because we are using phase modulation. So get rid of this, get rid of this. Also get rid of all these. All right? Okay. So at time is equal to 0, I guess you can, let me see here, m prime of t. Okay? So it depends on what situation you look at. So, if you're going from this way to this, it depends. So you can, either situation will be fine. It depends whether you're looking from the left or the right. So this could be 0 or 1,000, okay? At time is equal to 1, right? The derivative is minus 1,000. At time is equal to 2, it's 1,000. And then time with equal to 3, it depends on which way you're looking at. You can either do 1,000 or minus 1,000. It's up to you, but either answer is acceptable. So 1,000 or minus 1,000. It depends on which side, which way you're approaching from. 4 is going to be minus 1,000. 5, it's ambiguous again, so you can do 1,000 or minus 1,000. And then 6 is going to be, we'll just say it's 0. Actually, no, 0 or 1,000, that's fine. 0 or 1,000. Okay? So that'll be the situation there. So, okay, so in this case, if you want to figure out, this is not a, yeah, I guess it's a megahertz, that's fine. So you have the carrier and then added with 100. So if you had 100 here, so 1,000 times 100 will give you 10,000 again. So this will either give you 10 or 9.9. No, 9.9, it'll have, yeah, minus, no, sorry, it's minus or plus. Let me see what's going on. No, it'll be 0 or 10.1, I'm sorry. 10.1, right? Yeah, 10.1. Okay, so at 1, this will give you 9.9. At 2, this gives you 10.1. At 3, it'll either give you 9.9 or 10.1, depending on which situation you use. This is 9.9, and this will be 9.9 or 10.1, and this will be 10 or 10.1. Depends on which one you use. It doesn't matter. Either one is, either of these definitions are perfectly acceptable. Okay, so that is part B. Now we're going to take a look at part C. So plot the phase modulated signal and specify the important values on your graph. Okay, that's totally fine. So remember, the instantaneous frequencies are defined in this following fashion here. So all you have to do is, okay, so if you take a look, so between 0 and 0.5, you have your, 10.1 megahertz. Between 0.5 and 1.5, it's 9.9. So it's going to fluctuate between 9.9 and 10.1 and 9.9 and 10.1. Okay, so we're going to do that right now. So this is C. So what's going to happen is that between here and here. So this is your phase modulated signal. Okay, so let's mark important time points. So 1, 2, 3, 4, 5, 6. Okay, this is in milliseconds. All right. So between 0 and 0.5, there is your instantaneous frequency is going to be, we'll just assume it's 10.1. Yeah, so between 0 and 1, it's going to be 10.1. So this is, this is your height, which is 1. So it's going to fluctuate between -1 and 1. Okay, but what's going to happen is between here and here, you're going to get, some frequency like this, right? Oh, sorry. Between 0 and 0.5, so it's going to look like this. So between here and here, this is 10.1 megahertz. Okay? And between 0.5 and 1.5, it slows down a little bit. So it's going to look like this. Okay? So between here and here is 9.9 megahertz. Okay? And, oh, sorry, it's between 0.5 and 1.5, sorry. So this is 1.5 over here. All right, so let me just cross this out. So it's going to look like this. Slow down a little bit over here. So between here and here is 9.9 megahertz, right? And between 1.5 to 3, it's going to fluctuate at 10.1 again. So, okay, so between here and here is 10.1. Okay, and then between 3 and 5, it's going to go down to 9.9. So it's going to look like this. Slows down a little bit. All right, so from here and here, it's 9.9. And then finally, between 5 and 6, it goes back to 10.1. So it gets faster again. Like that, I guess. Actually, that's a little bad, so let me just... like that. Okay? 10.1. That's it. Okay? There you go. Now, if you want, let's do a little bit of a bonus. We can do frequency modulated if you wish. So what's going to happen is that you're using the message signal directly to modulate the frequency of your carrier. So as a bonus, let's actually go ahead and we will do the frequency modulated wave if you wish. Okay, so we can do that. And it's good practice because, something like this may happen on your final exam. It may not, but it's good to know. 1.5, and then this is 2, 3, 4, 5, 6. Okay? So how exactly this works is that the message signal itself varies the frequency. So what's going to happen here is that between 0 and 0.5, it's going to modulate between 10 and 10.05 because what's happening here is that, the amplitude here is 0.5, so the frequency will vary between 10 and 10.05. So it's going to start slow and then, so it's going to start slow and then start to increase. So between here and here is 10 to 10.05 megahertz. okay? And then between 0.5 to 1.5, it's going to slow down from 10.1 down to 9.9. So it's going to look like this. So it's going to speed up and then slow down. Okay? So between here and here is 10.05 down to 9.95 because you're going from from 1 to -1, and then oopsie. So here that, okay? And then between 1.5 to 3, it speeds up again, going from, this is 9.95 here, and then you're going up by a slope of 1,000. So this goes from 9.95 back to 10.1 because there's a difference of 0.15 megahertz. So what's going to happen is that this will speed up, and it's going to slow down, speed up again like that. Okay, so between 10.5 to 9.5, which is between here and here, right? And then between here and here is going to be 9.95 megahertz to 10.1 megahertz. So this is 10.5 to megahertz to 9.95 megahertz. And between 3 and 5, it's going to slow down. So it's going to go, so there's a difference of 2. So what's going to happen is then it's going to decrease by 0.2 megahertz. So it's going to go from 10.1 down to 9.9. Okay, so it's going to speed up and then slow down like that. So between here and here, this is 10.1 megahertz down to 9.9. Okay, and then finally going from 5 to 6, we're going to speed it up, going from 9.9 back to 10. All right, so it's going to simply look like, yeah, that's fine. It looks like this, like that. So between here and here, it goes from 9.9 back to 10. So the difference between phase modulation and frequency is that with phase, it's pretty much staying constant between the intervals. With frequency modulation, it slows up and speeds down depending on the actual message. So the message actually directly modulates your signal. Okay? That was just a little bit of a bonus. It's not required, but it's something to know in case something like this is asked. Okay, that's it. I've got a couple more questions. The first one is going to be a little involved. It's fine, but the fourth question, the last one, is going to be very easy. Should only take a few minutes. But I only have 2 more. We should hopefully get out of here by 8:30. Hopefully, and we should be fine. Okay, so the reason why I want to do this question in particular is because this directly relates to the pre-lab for lab number 3, where you have to actually sketch the FM spectrum for a single tone message signal. All right, so this actually is directly related to your pre-lab. So, yeah, so this is a nice review as well. Okay, so the spectrum, so actually you can ignore this pre-lab for lab 5. This was the pre-lab many, many years ago, approximately 10 years ago. So this is not the pre-lab for lab, there is no lab 5 for this course, so you can ignore this. This was lab 5 at the time when this course was offered, which is about 2007 or 2008. So don't worry about it being for lab 5. It's just a review question, okay? All right, so we've got a sinusoidal carrier that is currently unmodulated with a carrier height of √2, and the carrier frequency is 25 kilohertz. So this carrier wave is frequency modulated, so it's not angle modulated anymore. It's frequency modulated with a single tone wave with a frequency of the message as 2 kilohertz with amplitude A of M. So we actually don't know this, but this will be defined later on in the question. Also, the sensitivity constant, K of F, is 20 kilohertz per volt. So this is actually the units for the sensitivity. You don't need to know that. It's unitless, really, but the value is 20. The first question asks you, determine the values of the amplitude of the message signal that is required to give you the corresponding modulation indices. So beta is 1, 2, and 5. All right, so let's do the first question. If you remember, the modulation index is defined as the frequency deviation divided by the bandwidth of the signal. Okay, and the frequency deviation is defined as Kf M of P divided by let's see. So this is actually in hertz. So you don't need to divide by 2 pi anymore. So no need to divide by 2 pi. Okay. So because this is already defined in hertz, you don't divide by 2 pi anymore because it's not. So you don't need to divide by 2 pi. So no need to. So in this case, it's just simply 2,000. Okay, because they actually tell you that the message frequency, that is 2,000. So that's fine. So if Kf is equal to 20,000, so this is 20,000. This means that this is simply equal to this is equal to, and then this is A of M, right? So this is equal to 10 A of M. So if I want to figure out what the message signal amplitude is, I just simply have this relationship, which is beta over 10. So all I have to do now is I just have to substitute for beta is equal to 1, 2, and 5, and that gives me the required message signal amplitude that I need to respect these modulation indices. So for beta is equal to 1, AM would be 1 over 10, right? If beta is equal to 2, AM would be 2 over 10 or 1 over 5. And if beta is equal to 5, my amplitude would simply be a half. All right? So if you want it in terms of floating point numbers, if people like floating point numbers, it's 0.1, 0.2, and 0.5. Okay, so that's pretty much it. Okay, so we don't know what the message signal is, but we have desired modulation indices. So if you have this modulation index with this frequency that is defined for that cosine wave, it's either 0.1, 0.2, or 0.5, depending on what the modulation index would be. And that's it for that question. So A. So B, use table 1, please refer to, okay, again, I'll give you, so this table here, this table 1 is the Bessel coefficients, which is also part of your pre-lab, and I will also give this to you on the final exam, this table 1, to find the spectrum of the FM signal. So find the RMS value and location of each frequency component. So let's ignore the RMS value. We don't need to do RMS value here. Let's just find out what they are specifically. So ignore RMS value. So find the location of each frequency component. Okay, so let's ignore RMS value. We don't need to know that. Okay, so let's do that one. So this is B. Okay, so let's see here. So the modulation index 2. Okay, we're also going to use the 1% rule. Okay, we're going to use the 1% rule. So what the 1% rule means is that when you take a look at your Bessel coefficients, you choose as many coefficients as there are where the magnitude is 0.01 or more. Anything less than, you remove. Okay, so this is what the Bessel table looks like. All right, so this is what the Bessel table looks like, and this is for beta equals 2. So this guy over here. So this is the cusp. This is the point of no return right over here. Okay, so this is the, so you don't ignore these, so you're left with just, so there are 5 coefficients in total. Okay, so that's what we have. So we have, so at 2.0, so your Bessel coefficients at 2, basically there are 5 in total. Okay, so we have, let's see here, 0.22 for n is equal to 0. Okay, we also have 0.58 for n is equal to 1. 0. And then what we have here, 0.35 for n is equal to 2. Okay, and there's 2 more, 3, 4, and actually no, there's 6 in total. I'm sorry, not 5. So we have 3, 5, and then we have 0.31. Okay, so we have 0.13, 0. What's it? So 2, 5, 8, 3, 5, 13, 3, and 1. Okay, good. So come on. So 3 and 1. So for n is equal to 3. Sorry, can't write today. Actually, when can I ever write, I guess. So n is equal to 4, and for n is equal to 5. So there's 6 pairs of coefficients here. So that's what we have here. So, okay, so then how do you plot the spectrum? It's very easy. If you remember the equation for the Bessel coefficient, so for a single tone modulated signal, okay, this is equal to AC summation over, over n, right? Actually, instead of going to infinity, we're going to summation over all possible values of n. Bessel coefficients, and then cosine. We'll do this in omega. Okay, let's practice and let's do this in omega c. All right. Okay, so that's the Bessel coefficients integrated into your spectrum here. So in this case, this is the carrier amplitude. I'm given that already. This carrier amplitude is given to us as root 2. Okay, so this is root 2. This, our modulation index was equal to 2. All right. This omega c, this is given to us already. This was 25 kilohertz. So this is equal to 50,000 pi. All right. And this was, our frequency was 2,000, so this was 4,000 pi. Okay, because f of c here was 25,000, okay, and f of m is 2,000. All right, so if you took the Fourier transform of this, if you did this in terms of omega, all right, this is basically just a collection of different impulses. So when you take the Fourier transform of cosine in terms of omega, this becomes AC pi. And remember, we have just, it goes from -5 to 5. So n goes from -5 to 5, because that's what is defined for the table. Okay? jn of 2, because that's beta, and then you have cosine, and then we have, no, well, AC is equal to root 2, right? So let me just replace this. So this is root 2, and this becomes 50,000 pi plus 4,000, and this is n pi t, not cos, sorry, it's actually deltas, not coses, because I'm taking the Fourier transform, right? So this is delta omega minus, and this is 50,000 pi plus n 4,000 pi, okay? And then plus delta omega plus 50,000 pi, and oh yeah, and then plus n 4,000 pi. Okay, so there we go, all right? So this would be the equation. So all you have to do now is plot it out. If you remember the relationship between odd and even, right? If you had negative coefficients, right, it's equal to minus 1 to the n, positive. So this actually alternates back and forth between negative and positive values, all right? So this is the relationship that we have. So what we need to do now is we need to go ahead and sketch this. So so we're going to have, let me see here. So we're going to have 12 sets of impulses in total from n0, 0, 1, 2, 3, 4, and 5. So sketch this out. Okay, so actually what I'll do is I'm just going to do the positive part, okay, because there's not enough room here. So you can do the negative part on your own, it's totally fine. So we have, so you have omega c, and then we have omega c plus omega m, and then omega c plus 2 omega m, right? So there's 2, 3, 4, and 5. So 4, right? And okay, so let's just draw this through. And then finally this one here is omega c plus 5. Okay, so I'm just going to do the positive side. So positive side only. Positive side only. Okay? All right. So omega c, and then we have, let's see here. So this is, from here, this is omega c minus 5 omega m. Yeah, I guess I ran out of room here, so let me just adjust this a little bit. So let me go all the way out here. Okay, so we have 1 and then 2. This is omega c minus. This is omega c minus again. So this is 3, 2, and this is 1. All right? Okay, so we have different impulses here. So we have, so let me see here. So we've got, so each amplitude, so each impulse is scaled by AC pi jn beta, okay? Or in this case, it's 2. Okay? So here we've got an impulse that's scaled by root 2 pi, right? And then this is jn of 2. In this case, this is 0.22. All right, so this is 0.22. Okay? This here is j0 of 2. And then we also have 2 other impulses here. So we've got 0.58. So we've got the top. So there's one here. Also, there's one that's slightly higher here and here. Okay? So this one is root 2 pi, and this is 0.58. And also this is root 2 pi, 0.58. Okay, so this here and this here are j1 of 2. This is j1 of 2 as well. Now if you take a look at n is equal to 2, I have 0.35. So in this case, let's draw another one. So we have one down here and one down here. This is root 2 pi, 0.13. And this is root 2 pi, 0.13 as well. Okay, and then I have for n is equal to 3, I have 0.5. Oh, sorry, this is 3.5, not 1.3. Sorry about that. So this is 3.5, and this is 3.5 as well. Okay, and then down here, so we have 3. This is up, down here, up here, and up here. So this is root 2 pi, 0.13. This is root 2 pi, 0.13, and then we have 2 more to go. So you have one. Couple more like this, and each of them are 0.3 and 0.1. So we've got root 2 pi 0.01, and this is root 2 pi 0.03. Same thing over here. Root 2 pi 0.03, and this guy over here is root 2 pi 0.01. Yeah, I only had room to do the positive side, so kind of sucks, but it's okay. So this is what we have here. So that's the spectrum of your single tone modulated wave for the positive side only. And this here would be with respect to omega. And then you just repeat the same thing on the positive side and make sure that you respect this relationship here. But if I get you to sketch this on a midterm or exam, for example, just do the positive side because there's so many impulses you have to consider. Just do the positive side. I don't need you to do the negative side. So you have this, and then just keep that in mind for the future. Okay, so that's the case here. And then last but not least, we have this question. It says find the bandwidth of the signal when beta is equal to 2. Okay, well that's really easy, right? The definition tells us, remember that when beta is equal to 2, we simply have to count how many numbers there are. So whatever the number, so the maximum value here is going to be 5, right? So the maximum value here is simply, so n max is equal to 5. Okay, so this simply is it's equal to 5. And so we have 5, and therefore, okay, so this means that your bandwidth is simply, let's see here, twice n max, okay, times, let's see here, twice n max times the bandwidth of your signal. Actually, no, let's not do it like that. That's fine. No, let's forget that. So let's actually just use Carson's rule instead. Okay, so we can do twice. Okay, so in this case you have 2 times the frequency was, let's see here, this was, okay, so if we don't have this, so we don't have delta F, what you can use the alternative definition, which is this guy here, so 2b and then beta plus 1. So this is 2000, right? I know my modulation index is 2, so this is 2 times 3, which is 6, so we have 12 kilohertz as our bandwidth. Okay, so you can either use this or you can use Carson's rule. So one of these is perfectly fine. So you can use this or you can go to this if you don't have the frequency deviation, if you just have the modulation index instead. Okay. All right, so I've got one last question. It'll be very, very simple. Okay, it should only take a couple minutes and then we'll get out of here. Okay, so this is the last question I have for you. Okay, so last one. Okay. Here we go. Last question, I promise. So this is the last one. Okay, so we have a modulating signal, right? So what's actually happening now is we're presented the opposite. So we actually don't have to calculate the spectrum. That spectrum is given to us. So this is what the output of the spectrum analyzer would be. So imagine that we know that the input is a single tone wave, and this is what the spectrum looks like. So it is our job to figure out what exactly the parameters were so that it'll give us this particular spectrum if we assume that the message signal was a single tone wave. Okay, so that is the question. So a modulating signal AM, so we have an FM modulating signal 100, so this is the carrier, which is 100 here, okay? And this is done in, in terms of frequency modulation. So what we have to do now is we have to figure out what the peak frequency deviation is, the frequency of the message, and the carrier frequency. Okay, well that's pretty simple, right? Remember that when you are if you took a look at the Fourier transform at the top, you know that because it's symmetric, wherever the center impulse is will tell you what the carrier frequency is. So basically the carrier frequency is right here. That's this guy over here. So 500 kilohertz. Okay? Also the spacing in between each of these impulses, because this is a symmetric spectrum, basically if you took the difference between any one of these, it'll actually give you what the actual message signal frequency is. So it's just 1 kilohertz, right? That's good. All right. So now we have to figure out what the frequency, the delta F is. Okay, so if you remember what that is, so delta F is equal to K F AM. Actually, before you even do it, you don't even know that. We don't even, okay, so we can't even do this, unfortunately. All right? Because we actually don't know what the actual amplitude message is. So this we actually don't know. This, unfortunately, we do not know. We have to know what the message of the amplitude is, and that's not given to us. Well, it's actually pretty simple to do that, to figure that out on your own. So if you remember, remember the height of the impulse, right? So the height of the impulse centered at FC, okay? It's simply AC J0 beta over 2. Okay, this is in terms of F, all right? So if this is what we have, okay, all you have to do is take a look at the, let me see here. So where's our thing? So this is 38.5, all right? So this height here, so this is equal to whatever the height of the impulse is, which is 38.5. So this is equal to 100. So if I solve for this, I have to figure out where the N0 coefficient is that'll give me a modulation index such that the height is 0.77. Okay, so I have to figure out where on the table that is. So if you actually take a look at your Bessel table, so at n is equal to 0, you have to figure out exactly which height gives you 0.77. So in this case, it's right over here. So if that's the case, so beta is equal to 1, since J0 beta is equal to 0.77. So the modulation index is equal to 1. Okay, so therefore, beta equals 1. Okay, that's good. All right, so we have that. Now if you want to figure out what the frequency, you know what, let me see here. So delta F is basically, actually, so B, the modulation index is delta F over B, okay? So this is equal to 1, and then delta F divided by the bandwidth of the signal, which is 1 kilohertz, right? So therefore, your delta F is just 1 kilohertz. So that would be the answer. Okay, so this was from before. All right, so that's the first part. The second part is if AM is equal to 2.0, if the message is equal to, determine the frequency modulation sensitivity, K of F. Okay, so that's very simple. So delta F equals KF and then A of M over 2 pi. Okay, so K of F we don't know. Okay, this we know is 2. This we know is 1 kilohertz, right, from before, and this is 2 pi. So we got 2,000 pi equals KF and then A of M, which is equal to 2. So K of F is simply 1,000 pi. Okay, and that's it for that. So determine peak frequency, yeah. Okay, so C. This is a trick question, I'll tell you why. So sketch the magnitude spectrum of the modulated output if the message height was increased to 4 and the frequency of the message signal was increased by a factor of 2. Okay, so here, this is the reason why it's strict. So if you remember, the modulation index is defined as the deviation divided by the bandwidth, right? So if I want to calculate my new modulation index, right, because remember, the spectrum of your frequency modulated spectrum is dependent on the modulation index. So what this is telling us here is that if we increase our, if FM is increased by 2, right? So this is telling us here that this becomes 2B, right? And then if the AM is increased by 4, right? So this is telling us here that delta F becomes KF, and this becomes 2 AM, right? Because you're increasing the amplitude by 2, because you're going from 2 volts to 4 volts, right? So this becomes KF, and this is 4, okay? So this becomes 2,000 pi, it's 1,000 pi, okay? And this is 4, right, divided by twice the bandwidth, which is, what was the bandwidth? It was 1 kilohertz, so 2,000, right? So this is still equal to, let me see here, sorry, what's going on here? So we have 1,000 pi, so I'm going, so KP, so KP, and then we have to divide by 2 pi as well, I'm sorry. So what's going to happen here is you're going to have delta F, so this becomes KF, come on, so this is KF, A of M over 2 pi, right, and this is beta, B, right? So this becomes twice as much, right, and this becomes twice as much here, because you're increasing the amplitude by 2, because you're going from 2 volts to 4 volts, right? So in that case, these 2's cancel out, and you're still left with the same definition. So you're going to have 1,000 pi, and the message signal was A of M, so this is 2 volts, right, divided by your bandwidth, which was, what was it? It was, so of 1,000 kilohertz, right? And this is 2 pi again, so this is still equal to 1. So you increase the amplitude from 2 to 4, you also increase the bandwidth from twice as much. So what's going to happen is that since the modulation index is still going to be the same, the spectrum will not change. It actually the spectrum is actually the same. So since beta nu equals 1. Spectrum is the same. Okay, so basically it's gonna, it's basically just gonna look like the same as it was before. So let me just draw that out for you, and then we're good to go. Okay, so it's basically, let me see here. So we've got 1, 5.5, 2, 22. So we got 1, 5.5, 22, 38.5. So you have 1, 5, 22, 38.5, 22, 5, and 1. So this is 500, 497, 498, 499, 501, 502, and 503. So they're pretty much the same. It's the same spectrum. And this is an F. And that's it. Okay, so you increase the amplitude by twice as much, but you also increase the bandwidth by twice as much. So those two things actually cancel out, so you're still left with the same modulation index. So because that's the same, the spectrum is going to stay the same. Okay? And those are all the questions I have for you today. Are there any questions before you leave? All right, guys, so thanks for coming. We're going to finish up the course on Wednesday. We're going to talk about noise analysis, so hopefully I'll be able to finish within an hour, maybe hour and a half, and then we'll do some more review questions. Okay? So thanks for coming, and I'll see you next week.